In section 15.1, we integrated over rectangles. And 15.2 is supposed to be a little more generalized where it says integrating over general regions. For our purposes, we're going to think of general region as something that's not a rectangle. Because if you have a rectangle, you just have your limits on the length and the width, and that's it, right? And you just have numerical limits for both variables, and you just kind of go from there. This is a little bit more involved when it's not a rectangle. So when it's a shape like this or when it's a shape like this. But there are basically two options. And within that, sometimes you do have to do a little bit extra every once in a while. But overall, it's two basic ideas. Either like option one, which I think is the more intuitive one, where if R, the region that you're going to integrate over, is bounded by two functions of x. So that's what we've got here. We've got one function of x up here, so that's where it says y equals g sub 2 of x. We got a different one on the bottom, so g1 of x. And then as far as then when you're going to integrate with respect to x, there it is just a couple of numbers. So like the left bound and the right bound, so a and b are just supposed to be some numbers here. And then it's a similar idea with option number two, just the other way around, which I think at first is a little bit less intuitive, where if you were going to integrate with respect to x first and then y. In that case, you've got a function in terms of y as the bound on the right side of this region, and you got another one as the bound on the left side, right? There's h1 of y, here's h2 of y, and then the top and bottom are just some numerical bounds, right? C and D, that's all those are. Okay, so option number two is kind of the other way around compared to option number one. But then how do you actually do the integration? Well, here's Fubini's theorem again, but a stronger version, one that is for any kind of general region, not just a rectangle. So this here, and I kind of want these on the screen at the same time. There we go. This double integral right here, it's this picture on the left. Because this is the one where you've got functions of x as the bounds on the top and the bottom. So in that case, you would integrate with respect to y first, then with respect to x. That's why we got the dy dx right here. But then notice the limits with integrating with respect to y. There are those two functions. So it's still going to be the thing on the bottom is the lower limit, right? So in the picture, g sub 1 is on the bottom, so it's the lower limit here. G sub 2 is on top of r, right? That's its upper bound. Then that's going to be the upper limit of integration here. So that first variable that you integrate with respect to, the limits of integration are going to be in terms of the other variable. So these are both going to be in terms of x. And then after that, when you integrate with respect to x as your second step, then you just have numerical limits, right? Because a and b are just supposed to be some numbers. Other way around, what if you're going to integrate with respect to x first, then with respect to y? So it's like the picture that's on the right side. So notice that first variable that you're going to integrate with respect to, which here is x, then the limits of integration are going to be in terms of the other variable. And then if you're going to integrate with respect to x, you think the lower limit should be what's on the left and the upper limit should be what's on the right. Well, if we go up to where the picture is, that's how that's working. h1 is on the left side of this shaded in R, and then h2 is on the right side. So yeah, h1 is the lower limit, h2 is the upper limit. And then once you do that integration, then when you integrate with respect to y, the limits of integration are just going to be those numbers c and d. The notes toward the bottom, the first option where you have the dy dx, so integrate with respect to y, then with respect to x, our book refers to that as using vertical cross sections because you're integrating vertically first, right, with respect to y. And then the other way around is called using horizontal cross sections, because the other way around is this, where you have dx, dy. So you integrate with respect to x first, so you're integrating horizontally first. So horizontally first, using horizontal cross sections. For the first example, we want to first sketch the region of integration bounded by these three lines, and then write an iterated integral. Okay, so first thing is get the graph. That line is pretty easy, x equals 0, since that's just the y-axis. But then the other two, I think, for most people, they're easier to see what they're going to be when they're solved in terms of y, so that's what I did here. So I took the x plus 2y equals 2, solve that in terms of y, you get y equals 1 minus x over 2. And then for x equals 2y, you get y equals x over 2. Okay, so in the picture, there's x equals 0, right? It's just the y-axis. Then in order to graph y equals 1 minus x over 2, I said, well, the y-intercept is 1, so 0, 1's got to be on that. Then when you sub in 2, you'll get 0, so the x-intercept is 2. And 2 points are enough to draw a line, so I just drew in this line right here. Then for the other one, for y equals x over 2, I said, well, the y-intercept there is 0, so we're going to have the origin. And then when x is equal to 2, y is 1, so 2 1's got to be in there. That's enough to draw on that line. And where they intersect right there, that's going to be the point 1, 1/2. That's important because as far as for the outside integration, so the variable that you'd integrate with respect to at the end, you need those numerical limits, so knowing what that point is does certainly help. Okay, so if you were going to integrate with respect to y first and then with respect to x, which I think is the way that most people would sort of intuitively do it, or I think that would be kind of the way that feels natural, then you just have to look at this and go, well, then what's on the bottom and what's on top of this triangle? Well, what's on the bottom is this line here, which is really x over 2. Right? And then what's on top? Well, it's this other line here. It's 1 minus x over 2. So if I go down a little bit, there's my integral. So if you're going to go dy then dx, then the limits of integration for y, so for where that shaded triangle is, the thing that's on the bottom is x over 2. The thing that's on top is 1 minus x over 2. Right? And then you can see, just like we're supposed to have, we've got the limits of integration in terms of the other variable. And then for x, you just have to figure out, well, which x values are covered by that triangle. Well, it starts at x equals 0, because it's right up against the y-axis. And then it goes up to this point, 1, 1/2. So the biggest x value is 1, because that's the edge of that triangle, right? That's that point, and there's nothing past that. So, okay, well then the x value should go from 0 to 1. So then there are those limits. And then that's that. If you try to go the other way, like if you wanted to integrate with respect to x and then with respect to y, you get this thing, which looks a lot more complicated because there are 2 double integrals. And you think, well, wait, why are there 2 double integrals to begin with? Right? I mean, it seems like when we talked about it before, those formulas and theorems on the first page, it was just the one double integral. The reason for that, I have to go back up to the picture for this. When you would integrate with respect to x, if you're going to do that first, so then you want the thing that's on the left and the thing that's on the right. Okay, well the thing that's on the left is always this, right? It's always x equals 0. The thing that's on the right changes depending on if you're in the top half or the bottom half of the triangle. If you're in the top half, the thing that's on the right is this over here, which is y equals 1 minus x squared, which you'd have to solve that for x to get it phrased properly, but it's this line, right? It's this one that's sloping downward. But if you're in the bottom half of the rectangle, then the thing that's on the right is this. And that's this line, which is x over 2 or y equals x over 2, or I guess if you rephrase that the other way, which you'd have to do for integration, x equals 2y. What that means is that this part of the triangle right here, so I guess this lower part and the upper part, if you think about that in terms of y, it's like a piecewise defined function, where as long as y is less than or equal to 1/2, you're on this piece, but then when you're above 1/2, you're on this piece. So if you think about it that way, it's where it's like a piecewise defined function, then it kind of makes sense that you got to break the integral up into pieces. But you could also see it graphically just saying, oh, the thing that's on the right, sometimes it's this line, sometimes it's this other line, so we've got to break this up. So my first piece is the lower part, because notice I've got the y values going from 0 to 1/2. And there, when you go left to right, the left side is x equals 0, but the right side is x equals 2y. So right there's x equals 0, and then here's x equals 2y. And when you're in the bottom half, so between 0 and 1/2 in terms of the y values, that's the thing that's on the right. And then when you do the top half, the y values would then go from 1/2 up to 1. And then the thing that's on the right is this line, which is 2 minus 2y. Yeah, 2 minus 2y. So I've got the x values going from 0 to 2 minus 2y, and then the y values 1/2 to 1. So it's the upper half of that rectangle. And the reason I have things scribbled out is because I reflexively wrote those upper limits in terms of x instead of y, and I had to change it back. Which is really easy to do by accident, although if you were actually going to do the integration, you would catch it, right? Because then you'd have things that look like nonsense. But not doing the integration, it's an easy mistake to make, I guess. Example number 2 is a similar thing, where we want to write out an iterated integral, where r, now this is a little more complicated of a region. It's not all angular because we've got a parabola in the mix here. So bounded by the line y equals x minus 1, and the parabola y squared equals 2x plus 6. I rewrote the parabola as x equals 1/2 y squared minus 3 because it's easier for me to graph it by hand that way. Because then I can look at this and go, oh, the x-intercept is -3, and then you can kind of go from there. So the other thing I figured would be helpful is getting these 2 points. So where the line and the parabola are going to intersect. So for y equals x minus 1, I just squared it. So then y squared would be x minus 1 quantity squared, which is that. Because then I could set that equal to 2x plus 6, right? Because the parabola is y squared equals 2x plus 6. So I just said, okay, well, if y squared is this and then y squared is that, we should be able to set them equal to each other and then solve for x. And that'll give us the 2 points. Sure, because then if you have these two quantities equal to each other, ultimately you get that x squared minus 4x minus 5 equals 0, which factors. So then that means either x equals 1 or x equals 5. And then you can get the y coordinates. I guess the easy way would be by subbing into the line, right? -1 minus 2. Or -1 minus 1 is -2, and then 5 minus 1 is 4. So those are going to be the 2 points, and then drawing in the line is not too bad, right? And I plotted a whole bunch of points here, like 1, 0, 0, 1, -1, -2, let's see, 2, 1, 3, 2, I guess ultimately the 5, 4, because we know we're going to need that for the intersection point. And then to graph the parabola, I just got the x-intercept, I got these two, and then I guess that one, because we knew that had to be there since that's an intersection point. And that was enough to kind of draw in that parabola shape, which doesn't look great, but that's what it's supposed to be. It's supposed to be a parabola. It's enough to see what you're going to end up doing. Because if you try to do it as dy dx, where then you think, okay, well, what's on top, what's on the bottom? The thing that's on top is always the parabola. But the thing that's on the bottom, here it's the parabola, and then here it's the line. So you can do it as dy dx, but you'd have to do it piecewise defined and broken up into 2 separate double integrals. This one is actually easier if you go dx dy, because then you think, well, what's the thing that's on the left? What's the thing that's on the right? The thing that's on the left is always the parabola, and the thing that's on the right is always the line. So that makes it much easier, right? Any horizontal cross section you take, it's always parabola on the left, line on the right. So if you do this one dx dy, you only need one double integral. So that's this. So notice what I've got. So I'm going dx dy, then my limits of integration for x are going to be the parabola on the left, so that's the lower limit of integration, line on the right, so that's the upper, and I've got both of them solved for x. Right, so this we'd already solved for x, we know what that is. And then I've got y plus 1 up here because that's our line, y equals x minus 1. So if you solve that for x, you get y plus 1, right? X equals y plus 1. So that's what's on the right, so that's the upper limit. And then the y values, if you look at the picture, down here, the lowest point has a y coordinate of -2. The highest point is this one up here. It's got a y coordinate of 4. So that means that the limits of integration for y should be from -2 up to 4. So here, that's the easier way of doing it. I did write in the other way if you want to do it. So you can do it this way. I guess you'd have to solve for y as far as the equation of the parabola goes. So if y squared is 2x plus 6, then that'll give you two pieces that were individually functions but would not be a function if you combine them together into one thing, right? They'd fail the vertical line test. But you'd have the part that would be, I guess, the upper part, y equals the square root of 2x plus 6, and the lower part, would be y equals the negation of the square root of 2x plus 6. So then this part right here, where notice how the limits of integration for y are both the parabola, so it's like lower part of the parabola, upper part of the parabola, that's, if I go up here, it's from here to here. So between where x equals -3 and x equals -1, then the lower part is this lower part of the parabola, the upper part is this upper part of the parabola. So there's the lower part, there's the upper part, and then when you integrate with respect to x, this is just from where x is equal to -3 to where x is equal to -1. But then if you go farther, so from where x equals -1 up to where x equals 5, there, the thing that's on top is the parabola, but the thing that's on the bottom is the line. So then when you integrate with respect to y, then the lower limit should be the line, right? So it's y equals x minus 1, so then x minus 1 is the lower limit. The upper limit is the upper part of the parabola, so that's the square root of 2x plus 6. And then the limits of integration for x, it was where the x values were going from -1 to 5. So there's that. So this is one where the opposite way, or I guess what most people would think of as being the opposite way, dx dy, actually ends up being the way that's easier and probably faster. For example 3, we want to sketch the region of integration and then flip the order of integration. So we've got a dy dx here. We want to rewrite that double integral as a dx dy. All right, but first, graphing. So I guess in the back of your mind, I guess you want to think, okay, the x values are going from 1 to 2. And then we know the y values are going from 0 to the natural log of x. So the bottom of the shaded region should be y equals 0, which is the x-axis. And then the top should be y equals ln x. But we've only got to go from 1 to 2. Natural log of 1 is 0. So you go, okay, well then 1, 0. That's going to be part of this. And then that's going to go up to the natural log of 2, which is, what, about 0.693? Something like that. So there's the 0.2 natural log of 2. All right, so then there's the top part. So y equals ln x, just going from 1 to 2. Bottom is the axis. And then the cutoff is at 2, so we're just going to cut it off right there vertically because it says that that's where x goes up to, just up to 2. Right, that's the upper limit of integration. And so then that enclosed piece right there, that's our region of integration. And then over here, this is y equals the natural log of x, but if you then took both, or I guess raised e to both of these powers, you would get that x equals e to the y. I rewrote it this way because when we flip the limits of integration, that's how you're going to want it. So when you go in the other order, then if you look at where this is bounded, so left to right, so any horizontal cross section that you take, it's bounded on the right by x equals 2. That's the easy one. It's bounded on the left by this curve, which is y equals ln x, but if you solve that for x, that's x equals e to the y, like I've got it written there. So then that should be the lower limit, because that's the left bound, and then the right bound, which is x equals 2, should be the upper limit. And then the y values are going to range from 0, right, since this starts at the x-axis, up to ln2, right? That's the highest point right there of our region of integration, and that's its y-coordinate. So the y values go from 0 to ln2, and so that means on the outer integral, so the integrating with respect to y part, we should just have a 0 and an ln2. And then the left bound, so the lower bound going horizontally, was e to the y, and then the right bound, which would be the upper bound, would be x equals 2, right? So e to the y up to 2, and then 0 to natural log of 2 when you switch it to go dx dy. Example number 4 is another one where it looks like we're kind of doing what we just did, because we're going to sketch the region of integration, then we're going to switch the order, but then we're also going to evaluate the integral this time. And the reason that we're going to evaluate the integral, I guess other than the fact that this does come up a lot, is that this is one where if you try to do it using the order that's here with the dy dx, you're going to have kind of a rough time, because then you have to integrate the sine of y squared in terms of y. That's not simple. So this is one where it would actually be really helpful to switch the order of integration. the integration gets actually a lot easier if you do. So first things first, to draw this thing out, well, we know that y goes from x to 1. So that means the lower bound should be y equals x and the upper bound should be y equals 1. So here's y equals 1 up here, this horizontal line. There's y equals x. And then it says the x values are going from 0 to 1. So 0 is at the origin, there's 1, right? So it's going to be this triangle, right? With y equals 1 on top and y equals x on the bottom. Okay, well then the next thing is to switch the limits of integration around. So that's what we started out with. And now if we're going to switch to dx dy, then horizontal cross sections, any horizontal cross section you want to pick, the thing that's on the left is x equals 0. So that's the lower limit right there. And the thing that's on the right is y equals x or x equals y, right? Because you want to have it solved for x. So that's why I've got a y up there, right? Because then that line is always the thing that's on the right side of any horizontal cross section you want to take. And then the y values go from 0 to 1, right? The triangle starts down here at the origin. It goes up here to where y equals 1. So yeah, 0 to 1 for the limits of integration for y. And then this actually ends up being doable because then if we integrate with respect to x, you get x times the sine of y squared, double evaluated from where x equals 0 to where x equals y. Okay, well then really that just ends up being y times the sine of y squared. And this is doable, right? This is a u substitution within the trig function. So if u is y squared, du is 2y dy. So we're going to need a 2 in there with a 1/2 out front, which is what I've got right here. But then that's negative 1/2 times the cosine of y squared. Or I guess the way I've got it written here would be 1/2 times the quantity negative cosine y squared. But whatever, same thing. And then that's going to be double evaluated at 0 and 1. So you end up with negative 1/2 cosine of 1 minus a minus or plus 1/2 cosine 0. But cosine 0 is 1. So you end up with 1/2 minus 1/2 cosine 1. And that does it. If you try to do that one without switching the order of integration, that first integral, so integrating sine of y squared with respect to y, it's a bit difficult, right? So that's one where you think, I would rather not have to do this. And when you have double integrals, a lot of times this works. If you have a rough looking integration, you switch the order, you get something that's much easier to handle. Number 5, not the greatest parabolas that I've ever drawn in my life, but they're good enough to see what's going on, I guess. So the region that we're supposed to be integrating over is bounded by these two parabolas. So the one on the bottom is the 2x squared, right? Because 0, 0 is on that parabola. And then if you substitute in 1, you're going to get 2. You sub in negative 1, you're going to get 2. So that was enough to draw that one. And then the 1 plus x squared, there if you sub in 0 for x, you're going to get 1. So there's that point right there. Then if you sub in 1, you get 2. You sub in negative 1, you get 2. So then 1, 2, and negative 1, 2, those are the points where the parabolas are going to intersect. So it's this shaded in region here. Underneath 1 plus x squared and above 2x squared. So for this one, it looks like the simplest thing is to go dy dx because pretty clearly we can tell what's on top and what's on the bottom. So, right, it's 1 plus x squared's on top, 2x squared's on the bottom. So that's how I set this up. I said I'm going to go dy dx because I can see the top and bottom right away, where the bottom is 2x squared, the top is 1 plus x squared, and then the limits of integration for x. You say, well, the shaded part going left to right starts here at negative 1, then it goes over here to 1, so therefore my limits of integration are negative 1 to 1. And then you can integrate from there. So you integrate with respect to y, you get xy plus y squared, double evaluated from where y equals 2x squared up to where y equals 1 plus x squared. So there's the 1 plus x squared part, and then minus, there's the 2x squared part. And then there's a bunch of simplification. Eventually you get down here, and then those are all pretty easy to integrate, right? You get this here, double evaluated from negative 1 up to 1. And then here it is with the 1 subbed in, minus what you get when you sub in negative 1, which is all this stuff. And let's see, you get a bunch of stuff to add out. At least a couple of different things, right? The negative 1/4 plus 1/4, that's gone. 1/2 minus 1/2, that's gone. But then you get negative 3/5 times 2, you get 2/3 times 2, you get 1 times 2. So then negative 6/5 plus 4/3 plus 2. I got a common denominator and then added them together. And the least common denominator there is 15. So if you add those together, you end up with 32 over 15. And just to point this out, if I go back up toward the top, dy dx is clearly the way to go here, because if you don't, then you actually have to break this into 3 pieces, because then right, you have to like make a horizontal line here and say, okay, in this upper left piece, then you've got 1 plus x squared, right? It's that parabola that's on the right side, and then the 2x squared parabola is on the left. Then in this part, it flips around. Then in this lower part, it's this parabola on the right and on the left. So it's an ordeal. I mean, granted, you could use symmetry to just get one of these upper pieces and then to double it to cover the other one. But then you still have to do this lower part. If you went dx dy here instead of dy dx, you would create a lot of extra unnecessary work. That's really ultimately what I'm trying to say. Number 6, this is phrased a little bit differently, but basically you're doing the same thing. Volume of the solid underneath that paraboloid and above the region in the xy plane bounded by that line in that parabola. Okay, so this is basically the volume under the curve, because we're under this paraboloid but above the xy plane, right? So we're not going negative anywhere, which I suppose really you could say, well, how could you? X and y are both being squared. But still, this is the volume under the curve. That's the important thing here. And there are a few, and by a few I think I mean 3 on the list of homework problems for 5.2 that are kind of phrased like this. But we still kind of do what we've been doing, where first figure out what the region is that we're going to integrate over. So y equals 2x. Say, all right, well, that's at the origin. The point 1, 2 would be on it. I kind of missed here, so I had to redraw it. That's why that point looks weird. And then the point 2, 4. You can say, okay, well, there's that line. And then for the parabola, 0, 0, 1, 1, 2, 4. Right, so there's that piece of the parabola. And then it's this sliver in between the two, where if you look at this one, it looks like vertical cross sections and horizontal cross sections are about the same degree of difficulty, right? Because if you think about it as what's on top, what's on the bottom, for any vertical cross section, y equals 2x is on top, and then y equals x squared is on the bottom. But if you went the other way, dx dy with horizontal cross sections, the line, which I guess would really be x equals y over 2, that's going to be on the left side. And then the right side is the parabola, which I guess would be x equals radical y. So, yeah, I mean, there's not going to be a case where you have to break it up into multiple integrals. They're about the same level of difficulty. I did it the way that I figured most people would pick, at least the first way I did it was dy dx. I figured most people, when they see right away, like, oh, it's always the same thing on top and it's always the same thing on the bottom, they just kind of jump right to dy dx. That's what I do too. So I think for most people, that's kind of the natural way of doing it. But if you were going to do that, you'd say, okay, well, the line is always on top. So 2x would be the upper limit when you're integrating with respect to y. Lower limit should be the parabola, so x squared. And then the x values are going from 0 to 2. So there's 0 to 2 as the limits for x. And then if you do the integration, so integrating with respect to y first, you end up with x squared y plus 1/3 y cubed, and then evaluated from where y equals x squared to where y equals 2x. So here's the 2x part minus the x squared part. And then what we're going to end up with is, if you combine like terms, which you can do with those first two, you end up here with the 14/3 x cubed minus x to the 4th minus 1/3 x to the 6th. And then integrating that with respect to x isn't too bad, right? You end up there. Got to evaluate that where x is equal to 0 and then where x is equal to 2. Where x is equal to 0, you just get 0, right? 0, 0, 0. But then you just have to sub in 2's, I guess, for the x to the 4th, x to the 5th, and x to the 7th. And then this is another one where if you want to get a single fraction, you got to find a common denominator. The easiest one to use looks like it's going to be 105, right? 3 times 5 times 7. So then you get that common denominator, you do a bunch of subtraction, you get 648 over 105. And both of those numbers are divisible by 3, so you end up with 216 over 35. And just for completeness' sake, I did this one the other way too, if you went dx dy instead of dy dx. So you have to solve the line and the parabola both for x first. So you get x equals y over 2 and x equals radical y. And at any horizontal cross section you pick, the thing that's on the left side is going to be the line, and the thing that's on the right side is the parabola. So it's going to be y over 2 is the lower limit since that's on the left. Radical y is the upper limit since that's on the right. And then the y values go from 0 to 4, right? Because the upper point, like in the upper right of that shaded in picture, it's the point 24, so it's y coordinates 4. And then if you do the integration, it's about the same degree of difficulty. Even with the combining like terms in this step, you get 2 terms that you can combine just like in the other one. And then even, you get down here, you got to find a common denominator. It happens to be the same common denominator of 105, and you get 648 over 105 again, which reduces to 216 over 35.